This is section 3.2, Interpreting Computer Output Regression to the Mean. The first thing that the notes tell you to do is to read page 181 through 182 and look at the book example. And this was an example that you were supposed to look at from your previous set of notes. So hopefully you've already done that, but what I want you to pay close attention to is the AP exam tip, the box within the example on page 181. It gives you a really good fill in the blank for describing r squared. So whenever you have to interpret r squared, this right there is a good format to follow. So be sure that you're reading over it. So go ahead and read over the example that we're getting ready to do in our notes today. Go ahead and pause the video so that you can read the description and understand what we're doing. And what we're looking at is how to read and interpret computer outputs, which is this box that you see right here. So you need to be able to pick out your slope and y-intercept so that you can write out your least squares regression line, and as well as your standard deviation and r squared. So we'll go ahead and start with standard deviation and r squared. So the easy part is you've already probably figured out that's your standard deviation of residuals. And of course, this part right here is going to be your r squared. Your slope is going to be this number right here. Okay, so that is your slope. And your y-intercept is actually going to be the top number. So that is your y-intercept. Okay, and so anytime you have a computer output that looks like this, those numbers here, that's what you're going to be looking at. You can ignore pretty much the rest of what they give you. So when it's asking for the equation of your least squares regression line, define any variables you see. So what we're going to do is we will type that in. So that's going to be your y hat, and I'll go in and insert the hat here in a second. So it's going to be y equals 1.0028 plus 0.07083x. And you need to tell what your y hat and x are. So y hat is the predicted number of cups of soda expelled, just from this example. And x represents the number of Mentos that were dropped. Okay, so make sure when you are, it is a good habit to get into, make sure you're defining your variables. And then, so let's make sure we call this our y hat. That was a little thick there. Okay, so interpret the slope of the least squares regression line. So we have already had a little bit of practice with this already. So remember, you always talk about it in terms of x, whatever your x represents increasing by 1. Your y is going to be doing whatever number that slope is. So in this case, we would say for every Mentos dropped in a bottle of Diet Coke, 0.07083 cups are expelled. Okay. Now, the next question is just asking what is the correlation. So remember, we talked about this in the last set of notes. Correlation comes from r squared. So we know that our r squared is 0.602 from that computer output, and I just rounded. So take the square root of that to get your correlation, which is your r. So r squared is your coefficient of determination, while R is just your correlation. So take the square root of 0.602 and R equals 0.78. Now, one other thing that you have to keep in mind is whether or not this R is going to be positive or negative. Your R squared value, since it is a percentage and it's being squared, is always going to be positive. R can be positive or negative, so that is dependent upon your slope. Remember, your correlation is always going to have the same side as your slope. So in this case, since our slope is positive, our R down here is going to be positive. If our slope was negative, we would have to make that a negative. So don't forget to keep in mind your sign, and it's going to be the same as your slope. And then part D is a linear model appropriate for this data, and explain. So for this one, we would just say that a linear model is a decent fit for these data because there's no pattern to the residual plot. So look up at your residual plot on your notes. I don't have it on the video here, but it is on your paper. So there's no pattern. Now, what you do see is you see the vertical lines. And that's not really considered a pattern. The reason those vertical lines are there is because the amount of Mentos dropped for repeated experiments. So that's why you do see those vertical lines. You see the vertical lines on your least squares residual line on the left side there, the graph on the left. And then, so like for example, you have your Mentos dropped, like 2 Mentos were dropped 3 times because you see 3 dots there over the 2, and 3 Mentos were dropped 4 times. So compare that to the residual plot. You see those 3 dots there, that just represents the 3 times that they were dropped and the 4 times they were dropped and so on. Other than that, they are, it's a random pattern. Okay, so we'll go ahead and answer this question. So we just say a linear model is a decent fit for these data as there is no pattern to the residual plot. And you might want to make yourself a note just so that you can remember, when you do see the vertical lines, that's okay because it represents repeated experiments. So just make yourself a note here. The dots appear to be in vertical lines because of the amount of Mentos dropped for repeated experiments. Okay. All right, so moving on. Would you be willing to use the linear model to predict the amount of Diet Coke expelled when 10 Mentos are used? Well, think about, if you think way back to the beginning of chapter 3 that we did before Christmas, if you look, using 10 Mentos, well, the most amount of Mentos that we dropped were 5. So if it's talking about dropping 10 Mentos, that's going to be your extrapolation. So, and it's outside of our data. So you can, describe it those 2 ways. So we'll just go ahead and describe that or explain that. So no, because 10 Mentos is data outside our data. This would be extrapolation. And we can't depend on data outside of what's given because we don't know if the linear pattern continues beyond 5 Mentos. All right, so moving on, calculate and interpret the residual for a bottle of Diet Coke that had 2 Mentos and lost 1.25 cups. Okay, so if we are going to calculate this, we're just going to plug into our formula. So we know the actual, our actual is the 1.25. 2 is our X. Okay. Okay. Alright, so this is our x, and this is the actual. So what we need to get is the predicted, and then we'll use our formula where we subtract the actual from the predicted. Okay, so we'll do y hat. So just make sure you put a hat over that. I'll go back and do that here in a second. So 1.00208 plus 0.07083 times 2. And once you calculate that, we'll get 1.14. Okay, and now we subtract our actual 1.25 minus 1.14, and we'll get 0.11. So make sure you are double checking the math here. Okay, so we need to say a sentence. So the actual amount of soda expelled exceeded the predicted amount of soda by 0.11 cups. And then just make sure you put the hat over your y. Alright, so interpret the values of r squared and s. So to interpret the value of r squared, remember you can use that fill in the blank sentence on page 181. So in this case, we would just say we're using that percent. So 60.2% of the variation in the amount of soda expelled is accounted for by the linear model relating the amount of soda expelled to the number of Mentos dropped in the bottle. Okay, so that is our r squared. And then for our s, so that is going to be the 0.067. So we would say when we use the least squares regression, line to predict the amount of soda expelled using the number of Mentos dropped in the bottle, we can expect our predictions to typically be off by 0.067 cups. Okay, so that's how you would interpret your r squared and your s. Okay. All right, so then the next part, if the amount expelled was measured in ounces instead of cups, how would the values of r squared and s be affected? Explain. So if you remember, correlation is going to stay the same no matter what. So that's not going to affect anything. However, your standard deviations are measured in the units of y and x, so it is going to be different based on your ounces. Okay, so that's how that is going to be different. So we'll just type that in. Okay, and so since we're actually going from cups to ounces, you're going from like a larger unit to a smaller unit. What we're going to be doing is actually multiplying, and so that's going to make your standard deviation larger. Okay, so make sure that you take the time, there in your notes it says read pages 182 and 185. So pause the video, make sure you take the time to read through it. And so then our next question, how can you calculate the equation of the least squares regression line using summary statistics? So one thing that you do need to know is these formulas are on the formula sheet that you will be allowed to use on the AP exam. And remember that your least squares regression line will always go through X bar and Y bar, which, remember, that means your mean of those. So if you're not given the mean, what you need to do is calculate the means and standard deviation of X and Y. So if those are not given. And so this is, once again, what we're using is, y hat equals a plus bx. That's our least squares regression. And of course, r is our correlation. Okay. And so if you don't have those, make sure you calculate the means, because we've got to have the means and the standard deviation of X and Y. If you're given them, that's a little bit less work that you have to do. So the first thing that you actually find your slope first. And so that is going to be your correlation times your standard deviation of Y divided by your standard deviation of X. Okay, so that's your formula for finding your slope. And then to get your y-intercept, so that's your A, that is going to be the mean of Y, so Y bar minus your slope, which is your B, times X bar. So let's put that in parentheses. Okay. And then make sure you put Y bar and X bar here. So I'm going to fix that. So Y bar, because that means your mean of Y, and then X bar, because that's your mean of X. All right. So then the next part here, what happens to the predicted value of Y for each increase of one standard deviation of X? So what you may want to look at here, you may want to take a second and read over page 184, and that explains where all this comes from. And so what it basically says in summary, if you so read through it, it takes you through the formula, but if you read like close to the bottom, it talks about y hat is going to be your correlation times the standard deviation of y above the mean of y bar. So if we basically kind of put that into a formula, so y hat, make sure you put the y hat there, must be r times your standard deviation of y above the mean y bar. All right, so if I go back, so y hat and then y bar right here. All right, and so to elaborate on that a little bit more, we would say for an increase of one standard deviation in the value of x, the least squares regression line predicts an increase of only r standard deviations in the response variable y. Okay. Okay, so let's actually put that into practice real quick so that it makes a little more sense on how to use that. Because you'll be asked questions, what happens for each increase of 1 standard deviation of x, or 2 standard deviations of x, or 3 standard deviations of x. So it could be any standard deviations. So it's a pretty simple formula. So what we're going to do, we'll come back to what is regression to the mean. Let's look at page number 62 on page 196. So if you need to pause the video, you can flip to page 196 in your book. So you don't have to copy the entire problem down. And you can just do this problem on the back of your notes or a separate sheet of paper, wherever you've got room. So looking at that particular problem, it's talking about the mean height of married American women in their early 20s is 64.5 inches, and the standard deviation is 2.5 inches. The mean height of married men is the same age is 68.5 inches with standard deviation of 2.7 inches, and it gives you the correlation is 0.5. And so I've already went ahead and laid out this information. So the first thing that we're going to do is find the equation of the least squares regression line for predicting a full year change from the January change. And so the first thing we got to find out is we need to figure out what B is. Okay, so if we're going to figure out B, that is, remember, so that formula is going to be R, which is 0.596 times the standard deviation of y over the standard deviation of x. So we're going to have 15.35, and in this case we do not have to change the percent to you don't have to move your decimal, you can just leave it just like that. And the standard deviation of x, so 5.36. Okay, so we'll calculate that. Once you calculate that, you get 1.707. All right, then we can calculate our y-intercept. We can calculate A. So remember, that's going to be the mean of y, which is 9.07. And actually, there should be bars up here. There should be bars over those. So that's going to be 9.07 minus B, which is what we just found. So make sure you find B carefully, because if you can't get B, it's going to mess up A. And then times the mean of x, 1.75, which is 6.08. Okay, so now we've got our B, we've got our A, and we can write our formula. So we have y hat is 6.08 plus 1.707x. Okay, so there is our least squares regression line. All right, and so then the most recent thing that we just talked about, suppose that the percentage change in particular January was 2 standard deviations above average. Predict the percent change for the entire year without using the least squares regression line. Okay, so what we would say here, just using that last thing on that previous page, is since the value of x is 2 standard deviations above the mean of x, or you can just put x bar, the predicted value of y will be 2 times r standard deviations of y above the mean of y, or you can just use y bar again right there. Okay, so in other words, we'll do 9.07 plus 2, because it's 2 standard deviations, and then our R, 0.596, and then our formula, or times the, 15.35 for the standard deviation of y. Okay, so this is the formula that you're going to be using. So your 9.07, so the mean of y plus 2, and then the 2 comes from, because it's 2 standard deviations, and you do times r, which is 0.596, which was given, and then above the mean of y, or the standard deviation of y, so that's your 15.35. Okay, so that's how you're plugging that in there, and then that's going to give you 27.4% once you work that out. Okay, and that's just using that last thing that we did on that previous page. Okay, so to go back here, what is regression to the mean? So your regression to the mean, basically what that's saying is that your variables are always going to go towards your mean. In other words, if you have a variable that's extreme on its first measurement, it's going to tend to be closer to the mean on its second measurement, and vice versa. If it was, close to the mean on the first measurement, it's likely, it could be extreme on its second measure. Actually, a better way to say that is if it's extreme on its second measurement, more than likely it was closer to the mean on its first measurement. And that's just what the regression to the mean is. So with that being said, let's see here. So another way to think about that is, if you think about the first 2 tests that you took, typically the students who did really good on the first test will maybe score a little bit lower on their second test because they're getting closer to the mean of the mean of the class, and vice versa. If they didn't do as well on the first test, they're going to do a little bit better on the second test. So maybe they score closer to the mean on their first test, and then more extreme on the other one. Okay, so if we put this into words here, I'm going to move this to make sure we have enough room. So if a variable is extreme on its first measurement, it will tend to be closer to the mean on its second measurement. And also, if it was extreme on the second measurement, it was closer to the mean on the first measurement. Okay, and I actually have one more example I want us to look at together. So this is not on your notes, but if you want to jot this down, and you can just summarize it if you want to, so pause the video if you need to, and get this down. So what we're going to do is we're going to calculate the equation of the least squares regression using summary statistics, and we're going to do another one where we're using that formula, where we're going to predict the second test, or predict the second test grade from the first test grade. So on the first AP test, students had an average score of 82.3 with a standard deviation of 5.2. On the second test, the average score was 79.3 and a standard deviation of 7.9. So one thing that I like to do is establish what my variables are. So in this case, y hat is the second test, and x is the first test. Oops. And that just kind of helps me figure out what I'm using for my variables when I'm plugging everything into my formula. So the average here, so on the first AP test, so this is going to be my x bar, 82.3 is my x bar, and of course this is going to be S of x, my standard deviation. And then the second test, average, so that's going to be y bar. And then this is going to be S of y, because that's my standard deviation. And then, of course, there's my r at 0.93. Okay, so if I go ahead and find my slope, b, so that was r, which is 0.93. And then that's going to be standard deviation of y, which is 7.9, divided by the standard deviation of x. So standard deviation of x is going to be 5.2. And so when we calculate that, we get 1.413. Okay, and so now we're ready to calculate our y-intercept. So we do the mean of y, which is 79.3, minus our slope, times the mean of x, which is 82.3, and we get negative 36.99. Okay, so our prediction equation is going to be negative 36.99 plus 1.413x. And that is our prediction equation. And that concludes this set of notes.